This video is intended to do a synopsis of some of the stuff we've talked about already about motion graphing, as well as to extend that a little bit before we tackle some of the other work. So we've looked at 4 different types of graphs so far. 3 of them very similar, one a little bit different. So we looked at a position versus time, a displacement versus time, we've looked at a distance versus time, and we have looked at a velocity versus time graph. Okay, and so those are the 4 that we have done so far. And so what we want to do is just sort of list our graph facts that we know. For the position versus time graph, the most important thing we know is that the slope of this graph is equal to the velocity. All right. Slope being change in y over change in x, right? Or change in the vertical over change in the horizontal. So that would mean a change in position per change in time. That's exactly what the definition of velocity is, the rate at which position changes. Now, here we said that the slope was also the velocity, right? All right, there we go. The only distinction between these is here, the vertical intercept was equal to the initial position, and here the vertical intercept was always equal to 0, because after 0 time, I have not gone any distance from where I started, which is the idea of displacement. Position, I could just be at an arbitrary initial position with respect to our frame of reference. Distance versus time. The slope here was going to be the speed, right? And once again, the vertical intercept was equal to 0 always, because on a distance versus time graph, after 0 time, I have not traveled any distance. All right, and so that's the basics with these. We're gonna go into a little bit more depth in just a minute on those. Velocity versus time graph. What we know so far about this is that, I should start with, the slope is equal to the acceleration. Okay, we looked at that one graph. The velocity versus time, change in v divided by change in t, that is acceleration. We haven't talked about this, but the vertical intercept here, let's say if I have a graph that starts here and does that, this just says at t equals 0, what is the velocity? So the vertical intercept is the initial velocity. Now there's a third note that I want to put down here, and we'll get back to it in a couple of minutes, but there we go. Right, so a quick overall thing. If you know all of these things, you can read anything going on with a position versus time graph. Okay, so then the next thing I just want to talk about, or read anything with any of our graphs, just to focus on a position versus time graph. Either my position versus time graph is going to be made up of lines if it's linear, or it will be curved, right? Those are our 2 choices, linear or curved. It's either one or the other. If the position versus time graph is linear and the slope represents the velocity, on a linear graph, slope is constant, so this is what it looks like for a constant velocity. All right? And if it's curved there, therefore, that means that the slope is always changing, and so this must be for an accelerated motion. Okay? When we describe when we describe something moving at a constant velocity, I either want to think about that having a positive slope or a negative slope. Okay? So positive slope or negative slope, this is moving forwards, and this is backwards. Whatever forwards and backwards are on your declaration, whether it's east, north, south, west, right, left, in, out, up, down, whatever you have it. Whatever direction is forwards, that's your positive. Whatever direction is backwards is your negative. It doesn't matter. So on a curve graph, in the same way, we still care about whether the slopes are positive or negative, right? Because even if I have a curve, I can look at one instantaneous slope and say, well, that slope is positive. Or look at a different curve and say that that slope is negative, right? So this thing is moving forward, this thing is moving backwards, because that's what the slope says. But these are two different types of curves here. What I care about, as well as the sign of the slope, is the slope getting flatter, or is the slope getting steeper? If the slope is, now notice I'm not saying increasing and decreasing, because those are problematic words. Because remember, increasing means going from negative infinity to positive infinity. Decreasing means going from positive infinity to negative infinity. So that's not really what we care about. We care about whether our slope is getting flatter or steeper. If the slope is getting flatter, that means that the number that represents the slope is getting smaller. Since the slope is the velocity, but like just the number of it, that means the speed. So getting flatter means that this object's speed is decreasing or it is slowing down. But if the slopes are getting steeper, that means something is speeding up. Okay? So there you go. That's everything you need to know about position versus time graphs. Velocity versus time graphs. Here's the interesting thing about the position versus time graph versus the velocity versus time graph. On a position versus time graph, right? Actually, let's go back to this. On a position versus time graph, we actually looked at something like this. If I had, let's say, this random graph here and this random graph here, it's the same graph but just translated upwards. In the same way that we did this with two straight lines. These two motions are identical. The only thing that's different is their starting position. Meaning, on a position versus time graph, the location vertically on the graph does not describe the motion. It only describes where that object was at one moment in time, right? But these are the same motion. The reason why I bring that up is because of velocity versus time graph, the placement on the graph with respect to the time axis is critical for describing the motion. Okay? So if I'm looking at a velocity versus time graph, well, notice this. Let's say if I have 1, 2, 3, 4, and let's say this is meters per second. This is -1, -2, -3, -4. Here's why placement on the graph matters. If I am in the first quadrant here, that means that my velocity is positive. So if the object, or if the graph is up here, the trend is up here, so if trend is here, this object is going forwards. But if the trend is here, that object is going backwards. So the placement on the graph with respect to the time axis matters. So the last thing we need to know here is speeding up, slowing down, and constant velocity. So what would a constant velocity on this graph look like? Well, that's saying you're maintaining the same velocity over time, same velocity. That's going to be represented by a horizontal line. Okay, so speed up, slow down. So let's remember what it means to speed up and slow down. Speeding up doesn't mean that the acceleration is positive. Slowing down doesn't mean that the acceleration is negative. Remember, you speed up when the acceleration and velocity are in the same direction. You slow down when the acceleration and velocity are in the opposite direction. So let's use that. So let's say I'm moving forward but speeding up. That means that both my velocity has to be in the positive quadrant here, and the acceleration, which is the slope of this graph, has to be positive. That would look like a graph that looks like, I don't know, like that. But if I was speeding up while going backwards, that means my velocities are negative and my acceleration is negative, meaning that the graph is going to be in the fourth quadrant and the slope's got to be negative. That looks like this. So to describe that, if you look at this, it looks like the trend diverges from the time axis, right? It's moving away from the time axis. It's not a horizontal line, it's moving away. Then hopefully you realize that slowing down is just going to be the opposite of these things, that the trend heads towards time axis, okay? And so that's how we're going to be able to read our velocity versus time graphs. All the questions about velocity versus time graphs are where is the graph and where is its relation with respect to the time axis. Now, there's one last fact about a velocity versus time graph that we need to get. Let's say I have a constant velocity of 5 meters per second. So if I were to plot that, say 1, 2, 3, I don't know why I did 3 there, 4, velocity meters per second, 2.5, 5, 7.5, 10. Okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, t in seconds. So that's the graph there, boom. So if I were to ask you how far this object travels in those 5 seconds, how far? Well, we would use our average velocity is equal to displacement over time. Here, since the velocity is constant, the constant velocity is the average velocity, 5 meters per second, delta s over 5 seconds, delta x is equal to 25 meters. Okay, so nice and simple there, right? Let's say a different graph though. Let's say the velocity versus time graph looks like this. We'll just do nice and simple there, 10 seconds, and then, I don't know, 50 meters, and there you go. So that thing would have that thing had an initial velocity of 0 because it starts at the origin, and an acceleration of whatever the slope is, 50 meters per second. So that's 50 meters per second minus 0 meters per second over 10 seconds minus 0 seconds, or 5 meters per second per second. Well, how far does that go? Well, I could use my kinematic equation and then figure that out. The initial velocity is 0, that term zeroes out, 1/2. 5 meters per second. The time is 10 seconds, quantity squared. 10 squared, 100, half of that 50, that's 250 meters, right? So we have 2 examples. Now, here's what I want to say. I want to say that there is something about this graph that also says 25 meters. Hopefully you're seeing it, that if I were to make a rectangle here, that the area of this rectangle would be equal to, let's see, 5 seconds times 5 meters per second. That's 25 meters. Coming here, I have a triangle. Right, what's the area of that triangle? 1/2 the base, which is 10 seconds, times the height, which is 50 meters per second. And then you get 250 meters, and there you go. The area from the time axis to the trend is the displacement of this object, okay? And so that's our last graph fact. So I'm going to go back to the beginning and write that down. The area from time axis to trend is the displacement. Okay? All right. Just so that we're clear on that, let's say we have some sort of wacky motion that was made up of a bunch of parts. Let's say it did something like this. And I wanted to know what the displacement there is. Well, very simply here, it's the area from the time axis to the trend. So it's this area, and then this area, And then this area, and I would just break those up into little triangles and rectangles and find those areas. You'll notice here that this area is negative. Why? Well, the velocities are negative, so this is going to be a negative displacement, right? You might be saying to yourself, area can't be negative, area is scalar. But here the area means the displacement, and displacement is a vector. This is a positive, you probably didn't say it like that either. The positive displacement, and this is going to be a negative displacement, okay? So we don't want to be making random shapes. It's always from the axis to the trend in that interval. And there you go. Those are your graph facts.